Lesson: Activation functions and their impact on AI models. In the realm of artificial intelligence and deep learning, activation functions play a pivotal role in the development and effectiveness of neural networks. They are crucial in determining a model's ability to learn and make intelligent decisions. Activation functions decide whether a neuron should be activated or not by calculating the weighted sum and adding bias. This concept is not just theoretical. It has practical implications that can significantly affect the performance of AI models in real-world applications. One of the primary functions of activation functions is to introduce non-linearity into the model. This non-linearity is essential because most real-world data is non-linear. Without it, even a deep neural network would behave like a simple linear regression model, unable to capture the complexities of the data. The choice of activation function can dramatically impact the convergence speed and the ability of the model to generalize. For instance, the sigmoid function, once popular, tends to cause issues like vanishing gradients, making it less effective for deep networks. In practice, the rectified linear unit has become the default activation function for many neural network architectures due to its simplicity and effectiveness. ReLU addresses the vanishing gradient problem by allowing gradients to flow through the network without being squashed to zero. This ensures that the network can learn faster and perform better. However, ReLU is not without its drawbacks, such as the dying ReLU problem, where neurons can sometimes become inactive and stop learning entirely. To mitigate this issue, variants like leaky ReLU and parametric ReLU have been introduced, which allow a small, non-zero gradient when the unit is not active, thus keeping the learning process alive. Activation functions also come into play when dealing with output layers. For binary classification tasks, the sigmoid function is still relevant as it maps predictions to a range, effectively representing probabilities. On the other hand, for multi-class classification tasks, the softmax function is typically used. Softmax converts raw scores into probabilities, which is particularly useful for tasks like image classification, where a model must decide between several classes. In the context of practical tools and frameworks, TensorFlow and PyTorch offer built-in support for a wide variety of activation functions, making it easier for AI professionals to experiment with different functions and observe their impact on model performance. TensorFlow, for instance, allows for easy implementation of custom activation functions, providing flexibility to tailor models to specific needs. PyTorch, with its dynamic computation graph, offers an intuitive platform for debugging and testing new activation functions. These frameworks facilitate the iterative process of model optimization, allowing practitioners to tweak activation functions and observe changes in performance in real time. Case studies have demonstrated the impact of activation functions on AI models. For example, in image recognition tasks, the switch from sigmoid to ReLU as the activation function in convolutional neural networks led to a significant increase in accuracy and training speed. A study by Krzyzewski, Sutskever, and Hinton showed that using ReLU in their CNN model, AlexNet, not only expedited the training process, but also achieved state-of-the-art performance on the ImageNet dataset, thus revolutionizing the field of computer vision. Moreover, the choice of activation function can also influence the model's ability to handle overfitting. Activation functions like swish and mish, which are smooth and non-monotonic, have been shown to improve generalization by providing a richer gradient flow. These functions have been particularly effective in scenarios where the model needs to extrapolate beyond the training data, such as in generative adversarial networks and reinforcement learning. In terms of actionable insights, AI professionals should focus on experimenting with various activation functions during the model building phase. This experimentation is crucial because the effectiveness of an activation function can vary depending on the specific dataset and task. Tools like Keras, which is built on top of TensorFlow, offer a high-level API that simplifies the process of switching between activation functions, enabling rapid prototyping and experimentation. Furthermore, professionals should stay updated on the latest developments in activation functions. The field is continuously evolving, with new functions being proposed that offer improvements over existing ones. For instance, the recently introduced GLU has been shown to outperform RealU in natural language processing tasks, as evidenced by its use in the BERT model. Keeping abreast of such advancements can provide a competitive edge in developing state-of-the-art AI models. In conclusion, activation functions are a fundamental component of neural networks, directly affecting their learning capabilities and performance. By understanding the nuances of different activation functions and their impact on AI models, professionals can make informed decisions that enhance model accuracy and efficiency. Leveraging practical tools and frameworks like TensorFlow, PyTorch, and Keras can streamline the experimentation process, allowing for the rapid testing and implementation of various activation functions. As the field of AI continues to evolve, the role of activation functions in neural network design will remain a critical area of focus for achieving superior model performance and tackling real-world challenges effectively.